From the lecture, you know that if we have a capacitor C and the current going through the capacitor is going to be IC, and VC is going to be the voltage created by this current. So IC is C dVc over dt. So for capacitor, the relation between current and voltage is going to be like that. For inductor, L, if the voltage is VL and the current is going to be L, the voltage is going to be L differentiation of IL over dt. So these two formulas hold for charging and discharging of capacitors and inductors. Based on this, in this experiment, we're going to have square wave inputs. So for function generator, we set it to square wave, and we are going to have an RC circuit. So this is going to be a square wave, and because of the charging and discharging characteristics of the capacitor, we are going to see that the capacitor, when it sees a jump here, it cannot quickly jump, so it gradually tends to go up to reach the target. So let's say if it is 1 volt, is trying to gradually go up the voltage across capacitor, so to reach to the 1 volt. Again, when it sees a jump down, a fall, it's not gonna immediately fall, it's gonna gradually go down to eventually reach the target. Again, the same thing here, and we're gonna see this waveforms across the capacitor. This period is the period of charge, and this period is period of discharge. How long does it take for the capacitor to charge completely? Let's say if the time that took for the capacitor to reach the target is this much, so let's say this is T, this is 5 times, so almost 5 times of RC. So if you multiply R and C times 5, this is going to be the time that it takes to reach the target. RC is known as time constant. It's shown by the tau. So tau RC is time constant. Basically what it says if the capacitor is a big capacitor, it means C is high and it takes more time for the capacitor to charge. Or if the resistor is a big resistor, then it takes more time for the capacitor to reach the target on the top. The same thing for discharge. It takes 5 tau for the capacitors to completely discharge. Depends on if we are going to give time to the capacitor to charge or discharge, you're going to see different graphs. For example, if I feed a high frequency signal to the circuit, capacitor doesn't have time to reach there. So what happens? You're going to see something like this. It means that the capacitor is barely reaching the target, and you're not going to see the steady state part which we had here. So this part, we don't see it here. We don't see it here. So it depends on the frequency of the input signal of the function generator. We're going to see different charge or discharge graphs on the oscilloscope. For inductors, we're going to have the same scenario. So let's say if the input is square wave input, then I'm going to have the same graphs, which is related to storing the energy in the inductor and then releasing it at this cycle. So store and release energy. The only difference is that tau, the time constant, is going to be L over R. So again, remember the tau for RC circuit was R times C. Here the tau is L over R. This means that if the resistor is a big resistor, the tau is going to be smaller here, and if the inductor is a big inductor, the tau is going to be a large tau. In next part, we are going to show you the real circuit, how to implement an RC circuit. Please notice that in this experiment you may have to deal with polarized capacitors. The polarized capacitors are normally metallic type, and it has, like, the pins have polarity. As you can see in this picture, this is a polarized capacitor. This pin is the negative one. You can see that the negatives are here. You can they are marked as negative, and the other side, which is a pin that I have put on the other side, one of the holes above this gap, is the positive one. Please make sure that when you put the polarized capacitor, one of the pins is in this area and the other pin goes on the other side of the area. So they are separated by this gap here. So one pin goes here and then one pin goes here. So the pin that goes to the negative one is shown as negative. There is a curvy thing that you see, which is the negative part on the diagram, on the schematic. So this is something that you have to keep in mind to deal with the polarized capacitor. Normally when the polarized capacitors are kept in a different way, and if you place it in a wrong way on the breadboard, there is a possibility that they burn, or at some point, if the voltage is too high, if the reverse voltage is too high, they may explode. This is an example of RL circuit which is implemented on a breadboard. There are a few things that I want students to please keep in mind. First of all, make sure that, as you know from before, the two pins of capacitor and resistors are connected in the same column. So they're both in the same column, so they're connected. This is one of the common problems that I have seen. Students are putting the pins of resistors and capacitors in different columns. Another thing, make sure that the pin from the capacitor, the both pins, are connected in two sides of the gap. So this is there is a gap which is breaking the breadboard into two halves. So make sure that they are in two sides of the gap. And then when you connect the function generator, the red one and the black one, these black and red cables, are the cables coming from the function generator. Make sure the black is connected to the negative side of the capacitor. So this is the negative side of the capacitor, so make sure the black is connected to the negative side, and of course the red is connected to the other side of resistor. And then when you are connecting the oscilloscope probes, make sure the two grounds are connected to the ground, which is the black. So the black one is the ground, and because I have a metallic extension, then I'm able to connect the the ground of the oscilloscope to this metallic extension, which is conductive. And make sure you're not connecting, this is another common mistake I have seen from students, that these grounds are connected to another point. Make sure these grounds are connected to the negative side of the capacitor. So basically, if you can count, and that's one of the things that the student can practice in the lab, that count the number of wires connected to a point. So number of wires connected to the negative side of the capacitor, the polarized capacitor, is 3. So you have 3 wires. This is 1, this is 2, and this is 3. So they are connected, 3 cables or wires are connected to this pole. And then when you connect the other side of the probe, so channel 1 normally should connect to the input. So this is connecting to the input, which is the function generator, the red cable, and channel 2 is monitoring the output, which is actually the voltage across here. So this is RV out. So this is the way that you connect the oscilloscope to RL circuit. For the rest, for RC circuit, for the rest, the other configuration, RL, LR, only the location of C and R is going to be changed, or instead of capacitor you may have inductor, but everything else is going to be the same. In this video we are going to show you how to use oscilloscope to monitor an AC or even a DC signal. Oscilloscopes are playing a very important role in any electronic lab, because that's pretty much the only way to monitor a signal in real time, because you know the AC signals are keep changing, so you need a specific technique and device to monitor a signal which is keep changing. Most of the oscilloscope have 2 channels, including this oscilloscope, channel 1, channel 2. It means that at the same time they can monitor 2 signals at a time. Each channel is connected to a probe. These are called oscilloscope probe. Each probe from one side is connected to the BNC jack. We call this terminal or jack, we call it the BNC jack. And the other side of the cable is oscilloscope probe has 2 pins. One is the ground pin, we call it the ground connection, and the other side is the signal connection. You can see that I can pull down the signal connection, and then I can connect it to any point. So let's say I'm going to connect this to a pre-built signal in the oscilloscope. So this is used for calibration. I'm gonna connect it to this point, and then I can connect the ground even though I don't have to, but I'm gonna just show you that okay, this is the way that we connect the other one to the ground. But again, I didn't have to because it's already connected. The ground is connected inside. So right now channel 1, so this is channel 1, as you can see, is connected to a signal. So each channel has different knobs to configure the parameters, but the best bet from the very beginning to see the signal right away is to use a button that I normally call it the magic button. It's called auto scale, which is this button. And if I push this auto scale, I'm going to see the signal right away on the display on the screen. So what auto scale really does is that it does all the configuration automatically itself, so it's programmed to do that. So I don't have to go through all these knobs and set them so that I could see a nice signal like this. So what I see here is a square wave signal, which is normally used for calibration, and it's a built-in signal inside the oscilloscope. I just used it to show you how a signal is going to be captured by the oscilloscope. In fact, this signal is keep changing in real time, but to us it's a solid stagnant signal. Why? Because the oscilloscope is creating a signal which is running with the same speed as the input signal, and in this way it can freezes the signal on the screen. But let's see what other stuff that we have here. So channel 1, as you can see, the light for channel 1 is on, meaning that the signal is available there. You can turn it off or on by just pressing it. So if I press it, it's off and you don't see anything on the screen. If I press it back on, the signal appears again. There is a knob on the top which is called the volt division knob, and if I change it to right and left, see what happens. The signal is scaled to be shown bigger, like higher or more compact. So this is called volt division knob. Why? Because in oscilloscope the vertical squares that or blocks, let's call them blocks, the vertical blocks that you see are related to the voltage. And you can see on the top, if you pay attention to the top, when I change the knob, you see a light is turned on here to show the scale. So right now the scale is 5 volt, and then let's change it to 2 volt, it might be better. So right now the scale is 2 volt, and I have 1, 2 and almost 2.5 blocks. So 2.5 times 2 volts, which is a scale, it means that this signal from top to bottom is 5 volt. So this is a 5 volt peak to peak, because this is one peak, this is another peak. That's why it's called peak to peak 5 volt signal. Then there is another knob here, the little knob that is labeled by an arrow, and see what happens if I move it. You can see the signal is shifted to the top or shifted to the bottom. So you can move the signal up and down using this one, because sometimes you need to relocate the signal to any location that you need. Another important button is this big button on the top, which is called time division button. And see what happens. It's not a time division knob, actually, not a button. So if I move it, you can see the signal is either compacted or is expanded. So it depends on how many cycles we are going to see on the screen. Again, when I change it, look at the top of the screen, you see the light is getting on to show the time scale. So at this time, the time scale is shown as 200 microsecond. And then if you look at here, it means that I have almost 1, 2, 3, 4 blocks is covering from here to here, which is a full period. 4 times 2 microsecond is going to be 8 microsecond. It means that this signal has a period of 8 microsecond. If you want to measure the frequency, you have to inverse the period to get the frequency. So the horizontal blocks are the time blocks, and the vertical blocks are the voltage blocks. So there are all other buttons here, but the main one, I just showed you the main one. One of the things is a specific feature with most of the modern oscilloscope is a quick measurement. So look at the quick measurement button. What happens if I press? So if I press quick measure button, the light is going to be on, and on the bottom of the screen, in this part I'm going to show you how to use the function generator to generate the AC signal with the power supply that we talked in the previous part. you could only generate the DC signal, but if you need alternating source of voltage, then you need to use the function generator. So when you turn on the function generator, as you can see, the default is going to give you a sine signal, but you can switch to a square or ramp, which is a triangular shape of the signal, a pulse, or even generate noise. So let's stick to the sine and set the function generator to generate a sinusoidal signal with 10 kilohertz and 1 volt amplitude. So here you can see that the display is showing 1 kilohertz. If I want 10, I press 1, then 0, and then it's going to ask me millihertz, hertz, kilohertz, megahertz. So I'm going to press on kilohertz, and you can see that it changed to 10 kilohertz. For the amplitude, I'm going to press the button right underneath the amplitude, which is this button, and then it says 100 millivolt peak to peak. So I'm going to press 1 volt, and it's going to ask me volt peak to peak, millivolt peak to peak. I'm going to press volt peak to peak, and you can see that 1 volt peak to peak is selected here. And let's say if you want to send the signal to the output button has to be pushed. This is a common mistake by students that I have seen. They forget to press the output signal, and as a result they're not going to see anything at the output. For each button on the top there are 2 parameters, frequency or period. So if I click once on the button, one more is going to switch to period, so you can set the period rather than the frequency. So let's say I want to set it to 1, and then it's going as a microsecond, millisecond, so I can set to milliseconds. So now a sinusoidal signal with the period of 1 millisecond is going to be sent to the output. Also you can set the high level rather than the amplitude, or you can check also the offset. Offset value is the value by which the sinusoidal signal is shifted to the top of x-axis or to below x-axis. So it's no longer symmetrical on x-axis, but also it's got an offset. It could be a positive offset or it could be a negative offset. So if I click on the offset, you can see from the shape that what the offset means, meaning that how much the signal is up or below the x-axis on the 0 line. Also you can click on the square wave to give you the square wave, ramp. So every button which is on and the green light is active, it means that that button is going to show the type of signal which is going to be sent to the output. There are other functions on the function generator. One of the important one is sweep. With the sweep you can generate an output that sweeps the frequency from anything that you want at the beginning to the end, but we are not going to use it for this experiment, so we leave it for other times. There is also a knob here, so let's say if I check the frequency with the knob, so if I remove the knob here, so by moving the knob you can see that the value is changing, or you can simply choose the keyboard and enter the number using the keyboard, which is normally faster, but with the knob you can have some sort of fine tunings on the values. Again, please do not forget to push the output to send the signal to the output. Another thing is that the cable should be connected to the output BNC terminal, and what you get at the end is a cable. So I'm going to show you the cable. The cable on the thing has a red and black, and the red is the positive and the black is the ground, which should be used for your signal. That's about the function generators, and I hope you like this part. Thank you.